number 18 that happened a few years ago. Problems from stage 2. So a stage consisting of 2 days, each day having 2 problems. If you're watching either on YouTube or on Twitch, you should find problems in the description below the video, the link to the problems. And those should be difference, garbage, tree rotations, and temperature. I hope you hear me well. If yes, or if not, please let me know. Same if something will be wrong during a stream. Since I think a Code Forces round starts in an hour and a half, I will try to finish within that time, or maybe I will be done with solving problems until that, and then maybe there will be time for some extra questions. So the schedule of today's stream is to first this introduction. We must wait a little bit for other people to open the stream. In a moment we'll start, I guess, in the order that the problems are present here, difference, garbage, and so on. After, let's say, 2 problems, there will be a time for questions, like general questions about Olympiad. After every problem and during a problem, you can ask only questions regarding this problem. So if you want to, for example, ask for some advice or whatever, don't do it during problem solving, because, for example, when we are in the middle of a problem, because then it will just unnecessarily scratch the whole problem description. So hi everybody. So as I said, links to problems are in the description. Also, I've added links to my codes on GitHub. You will be able to find my codes for every problem. I made them today, like 2 hours ago. And I will talk you through those codes later. But first, of course, the algorithm, how to approach every problem. So we start with a problem difference. In this problem, we're given a string with characters A, B, and so on up to Z, so lowercase English letters. We should find a non-empty continuous fragment of the word to maximize the difference in the number of occurrences of the most and the least frequent letter in the fragment, and we must print that maximized difference. The length of the string can be up to 1 million, and let's analyze the example. So I will draw on the right. Okay, so for example, we had a string AA, B, B, A, B, A, B, and we can choose this substring, and it contains five letters A and 2 letters B. So the difference between the most frequent and the least frequent character is 5 minus 2, being 3. And this is the best substring here. The result is 3. So there can be, of course, some brute force that checks every possible substring, and we want to find a better solution. And what is the difficulty stage of POI? So the second stage is a qualification for the finals. Okay. What can we do here? Well, some idea would be to maybe consider every beginning of such a string and to try to get the best possible ending place, sorry. Second idea would be to maybe try to make our alphabet smaller. So what if alphabet is only A and B? Can we solve a problem in that case? So if alphabet is only of size 2, it turns out that it's indeed easier, and then we can move to solving it for the whole alphabet. So for now, let's assume that the alphabet just consists of letters A and B. And let's try to find that maximum difference. if, since so there will be some more frequent character, maybe a, and if we change every occurrence of a to +1, well, because it increases our score of interval by 1, and every b as, let's treat as -1, then we get a quite standard problem, almost a standard problem, where we are given a sequence of numbers and we are supposed to find a subarray with the maximum sum. This problem is indeed well known, and the most famous algorithm to solve that is called, I'm not sure about the pronunciation, but cadence algorithm. You can find that on Wikipedia. And it's some greedy algorithm that goes from left to right and will find that maximum sum interval. The thing is that this is not exactly a problem that we are solving right now. This is not a problem we're solving today because we care about the difference between the most frequent and the least frequent character. In particular, the statement says that those characters must occur within the interval. So we can say that we can choose this subinterval with only a's and say that here difference is free, even though the sum of values +1, +1, +1 is free. Instead, we want both a and b occur in this interval. So we must either know cadence algorithm and be able to modify that, or actually I will assume that we don't know this particular algorithm and we'll try to solve it on our own. And okay, what is a very good thing for what is a very good thing for intervals and for the sum of interval? Well, it's prefix sums. A lot of problems that involve sum in interval involve prefix sums, because if we compute prefix sums up to every moment, in particular we know the prefix sum up to this moment and prefix sum up to this moment, prefix sum being the sum of elements until here, then the difference of these two is equal to the sum of numbers in the blue interval. We can just subtract the two intervals. So if pref of I denotes the sum of values until I, then we can say that the sum in interval LR is equal to pref of R minus pref of L minus 1 minus pref of L minus 1. We take the sum up to element LR and we subtract the sum up to element L minus 1. And now, if you think about a code for this finding the maximum interval, one possible implementation is to iterate with R. It turns out to be easier to first iterate with R and then iterate with L and find the best one. So actually, if we consider some particular R, like this one, so this is fixed R, if we want to maximize this difference pref of R minus pref of L minus 1, since for our current R this first value is fixed, then we only want to care about this pref of L minus 1. And since the whole thing should be maximized, the second part should be minimized. Let me move it to the left slightly so my face wouldn't cover it. So is cadence algorithm the one which uses prefix sums? No, it isn't. So this is just an extra optional stuff that you can read about later that also could be modified to work here, but not necessarily. Instead, I'm talking about a different solution, the one involving prefix sums. Can you please move comment pop-ups to the other side of the screen? That's a good idea. Well, actually, I will just move my both my face to the left, maybe. Or just pop-ups. Okay, that should be better, I hope. So pop-ups just sometimes will cover the statement. Also, please remind me to modify the title of the current segment that is on the bottom of your screens. So later, if somebody watches the video later after the stream, he can more easily jump to a correct problem, binary search it. So now it should be difference instead of introduction. Does it work? I don't see it working. Okay, it works. So if we want to maximize this difference and we have a fixed r, then we want to just minimize this second part, prefix of L-1. And I forgot to move it to the left. So we basically look for the such L that pref of L-1 will be minimum possible. And that's it. Except for one detail that we again forgot, that the interval should contain both A and B. So to deal with that, for fixed R, what I want to do is so here I see an A. I want to find the last occurrence of B on the left. Here, it would be here in this case. And I want to say that interval must start here or earlier to the left. So L-1 must be among these values because L must be up to the blue point. So what I need is such L that is earlier than some index and has minimum possible pref of L-1. And this can be solved in linear time because we just compute prefix sums. Then we compute minima over those prefix sums to know up to every place to know the minimum. And then we iterate over R, considering every next R, and we ask about the last occurrence of the other character. That is, we can store that in one variable, store the last occurrence of B, and the last occurrence of A maybe. So maybe for a general alphabet it would be store last occurrence of each of 26 characters. And then ask about minimum value in some prefix of those already computed prefix sums. Then we will get an optimal L. And this is a working algorithm in linear time, O of n for alphabet of size 2 so far. Can we try all pairs of alphabets and then process a 2-pointers technique for every pair? So the solution is 26 squared times n. That's close to a correct solution. So this we have for alphabet of size 2. What we can get is we can iterate over every pair of characters, possible characters, so 26 square, and for each of them run that algorithm to get O of n times 26 square. That is worth a lot of points, but not the full points. So n is up to 1 million. It's a bit difficult here because the Polish Olympiad used to not show time limits. So here we don't know the time limit. I think at least contestants back then didn't know it. So it was hard to guess whether 26 square would fit within time limit, but likely it wouldn't. Otherwise, I guess organizers would put a smaller limit like 100,000 for n. So n times 26 square is nice, but not good enough. But actually, if we code it properly, it's not n power 26 square, it's instead just n power, sorry, not power, n times 26. So actually this is the complexity if we iterate over every pair of characters smartly. How to do it? So actually we don't want that. And this was for alphabet of size 2. And this is for alphabet of size 26. Let's notice that if we have a long string with random letters, they don't have to be random, but they are various letters, C, C, B, D, E, F, A, and we consider, for example, a pair A and B, then we only care about these particular indices. Only about indices that have characters A and B. We should skip other characters. So what about a solution that tries every character? So it iterates over A, the first character to consider, then it iterates over B, both from 0 to 25, or well, from A to Z. And here, inside, instead of linear solution, it only moves through the indices where A and B are. This should be a bit faster. For example, if string consists of equal numbers of letters of each type from A to Z, then on average the number of characters that we move through is n divided by 26. So if this part is O of n divided by 26, then we are okay, because we have 26 times 26 times n divided by that, and in it we will get our desired complexity, this one. But string doesn't have to consist of every character of equal number of times, and still the complexity will be only n times 26, because we can compute, we might call it amortized complexity. For every character, so let's say for a B, let's compute how many times it will be processed here. Well, we must iterate over this character in one of the two loops, either first one or second one. And for example, if it's in the second one, so if these two characters are considered here, I mean they are equal to this letter that we consider here, then here we have only 26 possibilities. So every character among these 26 square options for the two for loops, every character appears in only 26 times 2 pairs. So if you print pairs AA, AB, AC, AD, and so on, 26 times 26 pairs, character B appears in only 52 of them, or maybe 51, something like that. The same for every other character. So only this many times it will appear in a pair, so only this many times it will be processed here in the linear part of the code. So every character adds at most, is processed at most 26 times, O of 26, so the total complexity will be n times 26. Each of n characters in the string is processed only O of 26 times. And to make this easier to understand, let's go through my code for this problem. Codes you can see in the description below, either if you watch on YouTube or Twitch, both. There is Git repository. I must log in. Okay. And here are my submissions. So this is my code. And what I do here. I create a list of occurrences of each of 26 characters to be able to only process those. here I have a string from the input, and in the main function I read the input. I just have an assert to make sure that the length of string is equal to n. And then for every character at position I add it to the list of occurrences. So this character minus a will give me a number from 0 to 25. I push back the index I. So now occurrences of x stores indices where letter x occurs. Then what I do is I iterate over pairs of letters, over A up to 25, over B up to 25. And if the two letters aren't equal, then I maximize answer with a function consider that gets the two lists of indices. And this function consider, so it gets vectors A and B. Here const and reference just say that you don't have to copy these values and this will not be modified, and then the program is faster. If either list is empty, then return 0. We want both characters to occur. Then we merge the two lists of indices, replacing them with -1 and +1. And this can be done just like in merge sort, when we have two lists, sorted lists, and we want to merge them. Then sort isn't necessary. We just move with 2 pointers through them, like in merge sort. So this is just standard merging of two arrays, but instead of pushing indices into the new vector sec, means sequence, I push -1 for every element from list of indices B and +1 for every index from A. Now I have a sequence of +1 and -1. Here you can see commented just printing this sequence. I wanted to see whether it works fine for the sample test. Then I want to find the maximum sum of a subarray that contains at least one -1. I don't even force that it should have 1. If it consists only of -1s, then the sum will be negative. And for sure, the answer for a problem is not negative. Okay, now what we do is here I compute prefix sums. This is a standard implementation. Push 0, meaning prefix sum of empty prefix. Then every time push the last prefix plus a new value x, where x iterates the sequence sec. Then I compute minimum. So for every prefix, I want to know up to this moment what is the minimum prefix so far. So I know that. This corresponds to our, when we are at some place with R, we want to know the last occurrence of B, and we only care about prefixes, pref of L, up to this moment. So this is why we need that. An alternative would be to also move with 2 pointers here. When we move with R, with L we move to the last last occurrence of the other character, and we know we need that previous prefix, pref of L, up to this moment. So actually this pref of min is unnecessary, just a single variable would be enough. But here I think it's more convenient, as long as memory and time allows them. So it's just extra OFN to memory, and it's a bit slower than a solution with a single variable. And then answer is I start with 0. Last negative is that index of the last -1, so index of character B. Then I say if this character is -1, so B, then I update the last negative index of the last B. And if B existed at all in the prefix so far, so if this value is not -1, -1 means fake value, index -1 doesn't exist, so it means there was no character B so far, I maximize answer with prefix up to this position, so pref of R, minus that minimum prefix up to last negative. And here I have +1 because when I compute prefix sums in this way, so first I put 0 for empty prefix, then I add n more values, then actually prefix sum up to index I is stored in pref of I plus 1. Then I return answer, and in my main function I maximize answer with the returned value, and then I print it. This works fine, so you can find it in the Git repository, and also I've put there solution by organizers that is just slightly different. So this one actually is quite slow. It's hard to say whether it would pass back then, a few years ago, because I create a few unnecessary arrays, vectors actually here, and it would be better to just do something in constant memory, like avoid this. Actually, prefix sum also can be avoided if we just go one by one. We can store prefix sum so far as a variable and increase by a new value, a new element. So that's the end of the solution. Let's see if there are some questions. So a good approaches here would be to think about cadence algorithm, or to think about prefix sums, because sum of interval is sum of the difference between two prefix sums. Can you prove time complexity? I did that. I've shown you why every character is processed only 26 times. And now it's time to move to the next problem, that is garbage. I hope the title is updated, or maybe I should open OBS for a moment. Okay, it's updated. So the statement is quite long, so let me summarize it. We are given, I guess drawing would be best for that. So this was what's the difference? This is garbage. So we are given two graphs. We can take a look at the example. We are given first n, the number of vertices, and then m, the number of edges. And we are given edges between vertices 1, 2, 2, 3, and then they say their initial state, here it's 0, and then their final desired state. So here first 1 and 2 are connected with edge of type 0. At the end they should be connected with an edge of type 1. Let's say that type 1 is a dashed line. Then 2 and 3 are connected first with dashed line. So here it's type 1, and at the end they should be connected with type 0. Type 0, then 1, 3 is the same as 1, 2, so here it's type 0, here it's type 1. Then 2 and 4 are connected in both graphs with type 0, and so on. 2 and 4. So there are some extra vertices here, I'm not going to draw it. We must transform the initial graph to the final one by sending garbage tracks along some simple cycles. So for example, this is a cycle. It's a sequence of vertices without repetitions, such that every two consecutive vertices are connected with an edge. And when we send a track along some cycle, it will flip the state of every edge there. So by sending it here through this cycle of size 3, we would change the type of this into a 1, 1, 0, and we would get exactly the final drawing. It isn't forbidden to put multiple tracks if I remember correctly, it is allowed to put multiple tracks through the same route. It's okay. So it's easy to see that for every edge, what is important at the end is whether an odd number of tracks moved through that edge. If yes, then the final state, will be different from the initial state, because every 2 tracks that go along one edge will cancel each other. So actually, from the input, we can just see which state of which edges should be different. And so instead of drawing here those states, we just know that there are vertices 1, 2, and 3, and an edge between the 2 vertices means the initial state and final state in the input are different. So we must put an odd number of tracks there. I think in the sample, in the first sample, it would be just what we would get is just 2 disjoint cycles of size 3. So here a solution would be to put one track through this cycle and one through the other cycle. And but the situation can be more complicated. For example, now I think so. If these represent edges that should be moved an odd number of times, and if as an extra I will add these 2 edges, then I think there is still a solution. And one example solution would be to send one track, for example, like this, and then the other track maybe like this, so visiting 2, 4, 3 or some other order, and here 4, 5, 6 are connected in a different cycle. Also, we could use the same edge twice, but it will turn out that it's unnecessary. And now a good start here would be to think when a solution exists, so when it's possible at all. And the lemma that we want to prove is that the solution exists. Lemma. The solution exists if and only if every degree of a vertex is even. So 2 divides degree of I for every I. So the lemma is that if this is true for all vertices, then the solution exists, and only then. So here in this drawing, actually I skipped. Maybe there are also some edges, maybe for example between 3 and 5, I don't know, 2 and 5, those that don't have to be flipped, so their initial state is equal to their final state. And a short proof why we shouldn't use them at all is that so this is not entirely formal, but if we have one cycle that uses some edge and then some other cycle that uses the same edge, so this edge is used twice, then instead we could remove this edge from both cycles and move along one bigger cycle. Here, to prove it formally, we should say what happens with edges on these blue parts that also repeat, but we could remove all of them, actually. So the first fact is that we don't have to use edges that have the same state initially and at the end, because we can just remove them. If there is a solution using them, there is also a solution without them. So we can ignore those. And then back to our lemma about even degrees. So the lemma is actually that there it's possible to cover a graph with cycles if and only if all degrees are even. And if some degree is odd, then but you can read a lot about Euler tours. So Euler was a guy who first thought about that, and for maps of some cities he tried to find a path that goes through all vertices, or maybe through all edges. So these are Euler's path cycles. You can read about those. But if some vertex has odd size, so for example maybe 1 is adjacent to 3 vertices, then if we have let's say in some cycle when we enter 1 and we will exit it, we cover this way 2 edges. So always every cycle decreases the degree of a vertex by 2. We actually didn't yet prove that edges should be used twice or like more than once, but still after this, so 2 edges disappear. I mean, they turn into those gray edges that we don't have to cover because their state is already guaranteed to be the same. The degree decreases by 2, or at least the parity doesn't change. So at the end we will finish with degree 1. So no matter how you cover a graph with cycles, the sum of degrees, counting only those cycles, will be even, and every degree will be even. And to prove the other side of implication of the lemma, so if degrees are even, then find a solution, split the graph into cycles, we will just think about a solution. If we write a constructive algorithm that finds those, then it's a proof if it always works. Okay. And what a solution could be, just first in any complexity. It turns out that a greedy solution works that finds any cycle and says, okay, let's use that cycle. So if for example, a graph looks like that, 5, 6, and I want to add some edges to make everything even. Yeah. What I claim is that we can find just any cycle, maybe for example this one, these 3 vertices, and say let's print it. Let's say this is one of cycles we use, or just maybe this square, this cycle of size 4, because after that the number of edges will decrease and every vertex will still have an even size. And we know from a lemma that if all vertices have even size, then we can't find a division into cycles. So what we can do is we can start with in any vertex, let's say it's a 1. We go to any neighbor, we go to another neighbor, maybe here it would be to 5, to 4, and once we go back to the start, we say this is a cycle, remove it from a graph, repeat the process. Harder and more tricky thing is if, for example, we go in order 1, 2, 3, 5, 4, and then from 4 we go to 3, so the order is like that. Then we found a cycle 3, 4, 5. So we can say, okay, let's print that cycle and start again. So start from any vertex and find any cycle. So run a DFS until you get to a vertex that was already visited, what means you get a cycle. So you move along some path. You have, for example, you have vertices on a stack. Here it would be 1, 2, 3, 5, 4. Then if you see a neighbor that is already on that path, then you have a cycle. But actually, if you say that we remove these 3 edges that create a cycle and we start again, the complexity could be quadratic. I think this solution would be n times m, because pessimistically you could create a very long path, like 1, 2, 3, and so on up to n minus 3, and then find a small cycle at the end. If you remove it and repeat the process, maybe still you would have O of n complexity to get to some cycle, and then you only remove 3 edges. So as the smallest possible cycle, pessimistic case, is that you will remove a cycle with 3 edges, like this one, 3, 4, 5, 4. Then to remove all edges, you need 5 divided by 3 repetitions of that algorithm, and each of them works in linear time. It's hard. I guess it will be O of n on average, no, not O of m. But this is O of, so then the total complexity is O of n times m. And we must improve it. It's kind of standard thing. It was, I think now it wouldn't be used in an important competition like Olympiad in informatics, because it's, let's say, well known. So the solution would be just to not stop the process. So when we have on a stack those vertices 1, 2, 3, 5, 4, like we said, then we see that there is an edge from 4 to 3. What we can do is we can say, okay, this is a cycle. Let's remove those edges. So we remove these edges. So we wasted the number of operations we wasted, the complexity we wasted is O of just cycle size, because we get back from this. Actually, we leave the last number, this one. And from that, we try to continue our path. So from 3, maybe we would go to 6. So now a stack would be 1, 2, 3, 6, and so on. This way, we don't waste a long path that we created only to remove a small cycle, because here the number of steps we take back is just the cycle. And every edge at the end will be printed in one cycle. So the sum of cycles, the number of operations we wasted, is exactly O of m. And now from this, we get complexity just O of m, n plus m. And the tricky thing here is to remove edges, I would say, to get O of n plus m. It's hard to say again in this problem whether we can get n plus m times logarithm. Limits are big. I think 1 million for m. Where are there? Yeah, 1 million for m. And if you have times log, then it can be slow. Because the thing is, if you store the neighbors of a vertex as a list, then you must be able to remove something. If, for example, it's a vector, you can't remove just a middle element. So if you remove an edge between 3 and 5, and you are at 3, so okay, let's if you came from 3 to 5, then you know in the adjacency list of 3, so in the list of neighbors, where 5 is. So a number 3 has some neighbors, maybe 2, 5, 6, 4. If you had your DFS was in 3, it iterated over neighbors, and you know how you got to 5, and you can try to remove this like that. The issue is that also we should remove an edge from 5 to 3, because when edges are undirected, then we have an edge from 3 to 5 and from 5 to 3, and we don't know in the list of neighbors or 5 where an edge to 3 is. Also in vector, removing a number takes linear of the size of vector, actually the size of elements, the number of elements on the right, because all the elements are moved here. So to deal with that, with the complexity of erase on vector, we can swap this. If you want to remove an element from vector and you want to do it in constant time, what you can do is to swap this value to be removed with the last value, and then run pop back to remove the last element, what works in constant time. The downside is that the order of elements will change because the last element will jump to this position where the removed element was. Maybe you don't want that. Or you could you could store everything on a list. So double linked list is able to remove something in constant time, but then also there is a difficulty to know from 5. So for a 5, where is where in its list of agency is 3 to remove an edge from 5 to 3. So it can be done. What I did is I tried to, in my code, do a similar thing that I would do many years ago when I was a contestant. So when you don't know some structure for something, then at least what I did, I tried to simulate that with a vector. So I will show you in my code later how I did that. And so here, of course, what you can do is create sets. So store the neighbors as a set, but it's extra log, and also set is quite slow. The constant factor is not so small, and you can get time limit exceeded sometimes. Maybe so if possible, and if you see how to do it easily, try to avoid set and instead use something that will have constant time, or maybe log n but with smaller constant factor. For example, binary search or sort have usually quite small constant factor, while set is a heavy data structure. So yeah, this is what we do. Here, this is a kind of problem where it's good to, even after inventing the whole solution, to think for a few minutes how exactly to implement that. So this is what I recommend to you during a contest. Do you hear me at all? I think my internet went off. Was my internet, so was the video on for the whole time? Because for the moment it stopped working for me, but I hope there was no pause in the stream. So I recommend here thinking before implementing, because then you will save a lot of time during implementation. Awesome. I was afraid for a moment. So let's see the code. Submissions. And by the way, my mistake, so you can see that I found a mistake in a minute. My mistake was that so when there is no solution, we should print nie, which means no. And when there is a solution, what I printed was I printed yes tag, and then the division into cycles, while there is no yes here in the output. So we print no only in the case of no. That was my stupid mistake. So be careful about that yourself. So what I did, I read the graph, and when I read edge between A and B with initial state S1 and final state S2, only if they are different, the states are different, then I run add edge. It's a complicated function. We'll move to that in a moment. Then for every vertex from 1 to n, if the degree is odd, then we put no and return 0, end the program. Then for every vertex starting from 1, if it has some edges, so if degree is positive and I didn't process it already, so not done, then I run DFS, and at the end I print cycles. Cycles I store in a global list of lists, or vector of vectors. And now, so later we'll care about this add edge, remove last edge. What happens in DFS? I have two Boolean arrays. On stack means that it's on that path that I started from the starting vertex, and done means it's completely processed. You don't have to go to that vertex anymore. when I have DFS in some vertex, I say on stack of this vertex is true, and also so far is exactly that stack. So it's global, and I just push back to that. At the end, if I go back from this, I go on stack of A is false, and I remove from the stack the last element. Now, so I usually in DFS we iterate over neighbors. I wanted to be able to easily remove the value, so I thought that maybe I could do it from the end, because if I take the last neighbor on the vector, then I can pop back that easily. So here I take B as a neighbor that is the last in the list. If B is -1, then just remove this thing and move to the second last element. -1 means that this edge was already covered. So in a moment we'll go to function remove last edge, where instead of removing explicitly from a list, I just change some value to -1, what means this is removed. When you later meet this, remove that. When here iterating from the end. Then if not this happened, then apparently this edge is available. I remove that edge, and I remove it. Then if B, the neighbor, is on stack, so on that path that we started, then apparently we have a cycle. Then I mark as a global variable start, that is here, starting vertex of the current cycle. I mark as this vertex to which I go. I create a new cycle, I push back to that A, and I break from a while loop, what means just remove, get back from this DFS. On drawing, this would look like that. When I have some, let's say, starting vertex 1, then 3, then 4, then 5, 6, and let's say from 6 there is an edge to 3. So now when I have, when 6 is A, and 3 is B, so I'm right now in DFS of A. I see that B is my neighbor, but it was already on the stack, because the stack right now contains numbers 1, 3, 4, 5, 6, and I'm right now here. Then I say, okay, I know that a cycle starts. I put A to the cycle, so cycle first I put A, that is 6, and then I also remove this edge to know this is covered already, and I get back from DFS, so I get back here, so break from this DFS. This one should also put its value to the cycle 5 and get back. Get back means just return from this recursive call, and your parent, the one who started you, will now be present, let's say. Then for also is added to the cycle. Also these edges are considered done already, processed. Then for a free I check, so here I check if start not a break, otherwise, so if start is exactly me, so at this moment when I'm in DFS of A, I put that global variable start as B. We did that here. Start is equal to B. So this is start. Now, when I finally get back to this place, I know that cycle is done. I put the last value here, and I'm done with this cycle. And I continue the process. So from 3, maybe I would go to some other neighbor 7 or whatever. And the number of times I got back, what is a wasted time, is equal to the cycle that I found. So the number of edges removed. So this is why the total complexity will be O of M. That's it about the code. This is a time for questions. So free for a moment. If you have some general questions or questions about the last problem, any of the two problems we already considered, then now it's the time. And later we'll move to the last two problems. So while this, let's say, break happens, I will once again say that in the description you can find links both to problems, to my implementations of problems we talk about today in Git repository. Also, if you want to follow me on Twitter, Facebook, you can find links there. I post reminders about my streams and YouTube videos, and also sometimes some extra posts about a problem or two, usually easier ones. And if there are no questions, then we move to the next problem. The next problem will be, let's see. So now it's time for two harder problems, temperature and tree rotations. I would prefer to first talk about temperature because it's easier. Also, so I will turn on the light. But maybe let's go in the order to make everything easier to find. I'm not sure. Okay, let's do task rotations. So now it's for task tree rotations. And now the problem is we are given a binary tree with values, so with the number of leaves n is up to 200,000, and leaves are, like, the values in leaves are is a permutation of numbers 1 through n. So if there are 3 leaves, the values are 1 to 3 in some order, and the values are different. It's a permutation. Now, what we must do is, for every vertex that is not a leaf, we can decide whether we want to swap the two children, and at the end we want to minimize the number of inversions in the corona of the tree, corona being leaves from left to right. So this is 3 rotations. Now, if let's draw a tree in a standard way, so a root is in the top. So let's see, let's consider this tree. 2, 1, 4, 3, 5. So here we see n equal to 5 leaves, and what we can do is, for any vertex, for example maybe this one, to swap the two children. So now if we flip this vertex, then it would look like so 4 is here, and on the right there is 2 and 1. And here, let's say we don't swap anything, so it's still 3 and 5. At the end, we care about the sequence of the sequence of values in leaves. So in this first case, it would be 2, 1, 3, 4, 3, 5. Just a sequence that a DFS or whatever would print if we prioritize going to left child first. Here this would be 4, 2, 1, 3, 5. And we want to minimize the number of inversions. Inversion is a pair of elements such that the one on the left is greater than the one on the right. So in particular, a sorted array has 0 inversions. And so an array sorted decreasingly has n choose 2 inversions. N times n minus 1 divided by 2. And yeah, So we must decide about the swap in every vertex and print the number of inversions. How to do that? It's important to notice that vertices are independent, like the swaps. Actually, first we should think, you should know how to compute inversions in a sequence at all. And one of those algorithms is doing that while doing merge sort. So you can split an array into two pieces, equal pieces, or like different by one, then run recursively for each of them. This would produce sorted pieces. And then while merging them in merge sort, we use two pointers, and for every element, so when we are here, when we add this element, we are here, with the second pointer we are here. For every element from the left, we know how many elements on the right we already processed, so we know the number of smaller elements in the right part. And this way, for every element here in the left part, we know the number of smaller elements here, so we know this way we can compute in the process the number of inversions, the number of pairs where number from a first half is greater than from a second half. And in merge sort we run recursively, so inversions inside each half will be already computed. And here we can do similar, that just not dividing into equal halves, but into non-equal parts. So for the root, for example, we know that on the left we have values 2, 1, 4, on the right it's 3, 5, and we just decide which one should be on the left. That's it. That's everything that this flip is about. Also, it doesn't affect other vertices, what happens in other vertices. So we can just so we have some lists L and R, values on the left and right. We can compute the number of inversions X when they are like that, so L on the left, R on the right. And then either we'll have this, or we will have the size of L times size of R minus X inversions. Because if we swap the two lists, so we swap the order of children, then each pair that was previously great in any inversion, now it is not an inversion because we changed smaller to greater, we swapped. And the same for things that were not an inversion. So each of L times R pairs, this means the size of list L, is like flipped. If it was an inversion, now it's not. So if there were X inversions, now it's L times R minus X. I think the technique called segment remerge can make the complexity n log n. I'm not sure what this technique means. I have written n log square solution, but I think there is a better solution. Yes, there is a better one. Okay. So what is the complexity of this algorithm? Well, if we merge in size, usually we merge in complexity size of one list plus size of the other list, then the total complexity will be O of n squared, because we do n merging and each of them can be O of n. And this happens when all the time a tree is very long and it goes to the left all the time. So a root has a right child being a leaf, then the next vertex the same. So a tree looks like a long path like that. Then you will get n squared complexity. What we can do instead is use the smaller to greater technique. I'm not sure about the proper term for that. So it's smaller to greater technique. well, where if we want to merge two things, we iterate over elements in the smaller of the two lists or structures, and we add to the other one. Now we can do a merge sort like that if we have a proper structure. So if I have a long list like 1, 3, 4, 10, 15, 20, 21, and I have a shorter one, just has 5 and 16. I want to merge those in complexity O of, well, this is size R, let's see. So this is R, this is L. I want to do that in O of size of R times logarithm of L actually. So let's say that it's logarithm of N. If this is for, if every list is stored as a set in C++, set, then we can take a 5 and insert it into a set, take a 16, insert into a set, then we would get R log n. And the smaller to greater technique uses the fact that every element will be added to a greater set at most logarithmically many times, and from that you get that the total complexity is n times log square. What we can do with set is we can say what is the number of elements smaller than something or greater than something, what we need here to count inversions. So we either have to implement our own data structure that allows it, some complicated tree, maybe dynamic segment tree, maybe, yeah, I guess it should be some dynamic segment tree. But there is a thing in C++ that allows that. It's called ordered set. And I will show you my submissions, so my submission. So this is, first I got time limit exceeded because I just created two great arrays, two big arrays. So there are a few magical lines in C++ that I advise you to memorize them before, for example, the second stage of Polish Olympiad. This is what people do. So there are a few magical lines that allow you to use something that is ordered set. It's a set with extra functionality. That functionality is to ask about the number of elements smaller than something, and also the kth smallest element or greatest. So if in that set you have elements 10, 20, 30, 40, 50, and you ask about the third smallest one, it will return you 30 in O of log time. This structure is quite heavy and the constant factor is big, but when I submitted it here today, it was accepted. I'm not sure it would be during a contest. Also, like back then, machines were different, maybe time limit was different, I'm not sure. So I think this deserves some points, but not the full score. And in a moment, I will talk about a better solution. But here, let's go through this code. So I create an array of these ordered sets. Actually, previously I put size 10 to the 6 here, and since time limits here are stupid now, like 0.1, not stupid, but very small, creating so big array already time limit exceeded for me. So I had to decrease that to 200,000, and it was then okay. I got accepted, 100 points. What I do is in main, so the description of the input, the format of input is kind of strange. It's recursive, where when we want to read description of some tree, we read a number. If it's greater than 0, then apparently it's a non-leaf. If it's greater than 0, then it's a leaf, sorry. And then I take just the next available array here. So next to take is a global, let's say, pointer that says which is the next array I can take. First it's 0. And to that ordered set, I insert x, the value in this leaf, and the function recursive returns the index of this set. So when I ran the course, I ran, well, DFS on a tree, and I expect that every vertex will return an index in this global array where my set is. Now, otherwise, so if it's not a leaf, then L is the left tree, the left child, R is the right child. Pairs is just the product of sizes. Then, to do smaller to greater technique, if the first thing is greater, if the first set is greater than the other, then I swap the two indices, L and R, because I don't care which one is which. I just want L to be smaller. Then, for every element in L that is smaller, I increase the number of inversions by this, what means the number of elements strictly smaller than A, because when I merge two things, I have this on the left, I have 5 here. I wonder what is the number of elements smaller in the right part. And this is what order of key does for ordered set. And then for every element in this left list, I add it to the right list. So this is complexity of that is O of size of left list times log, but then I clear that. And because it's smaller to greater, the total complexity will be only 1 extra log, not n squared. And I increase the global answer by the minimum of either the number of inversions I counted or the product of sizes L and R minus the number of inversions. And that's n log square of n solution. And it's possible to do it faster in n log n. Normal segment tree also works, not dynamic. The thing is that depending on the implementation, I can't create the segment tree of size n for all the vertices, because then it's n square memory. It's possible to do it with this on tree technique plus range queries. I agree. So this is also what I first thought about today when solving this problem. So there is something like DSU second tree. I will put a link in the chat for everybody. And you can read about it later. And it's something that when you have to run DFS on a tree, you go first to smaller children, then to greater. And because of that, you can just store one structure instead of like I had an array of structures. Then that, let's say, greater half will be not recomputed. This is a very short description. You can just read this block and try to apply it to this problem. And finally, what the intended by organizers did in this problem was to create dynamic segment trees. So what we can do is, let's say that n is equal to 4. Then we can create a segment tree with 4 leaves. And then on that segment tree we can ask about the sum in some interval, something like that. So if we know that there is an element 2, so there are possible elements are 1, 2, 3, 4. So this leaf corresponds to element 2. If we know that this structure should hold a number 2, then here we store 1, like our plus 1. It's also plus 1 here and plus 1 here, to be able to answer the queries about the sum in interval. But not to have n square memory complexity, because we don't want to store this tree in the whole tree for every vertex. We just store it in, we only store what is non-zero. So instead of that, we would just store the root, the left child, and this one. We would store 1, 1, 1. And also there would be pointers to null here, null and null. This way, if you have x leaves that exist, then the complexity, the memory complexity, will be of x times log of n. Let's move that to the left. Okay. So now the memory is fine, and as a next, so when you merge two trees, again you can do smaller to greater, and you would get x log square, one log because of a tree, one log because of a smaller to greater technique. But if you merge them smartly, you will get O of n log n total complexity time. So our goal is to get O of n log n. Sorry, 3 rotations. Where am I here? So how to get n log n with merging trees? Well, if we want to merge two trees, like this one and this one, then we run a recursive function that gets pointers to first the roots, and then we recursively run below. So then, for example, when we run to the left, we have these two vertices, so we add the values there, the sum of elements below. Then we see that there is a value here, so we copy that here. There is a value here, so we copy that here. But to get better complexity, when we are here, so we know that there is no vertex here, then we don't go below recursively. We instead just copy this pointer. So this thing is copied here. We don't go recursively below. And it turns out that the total amortized complexity will be n log n. How to prove it? Often amortized complexity you prove with some potential function or potential value. Here it would be the sum of sizes of those dynamic segment trees. So initially, for every leaf, initially you create a segment tree of size log, because there is one leaf that is turned on, set to +1, and a path to that leaf is it exists in memory. So you create that. So the initial potential P, again my face covered, sorry, a bit of drawing. The initial potential P will be n log n, and P is the sum, so this is like P0. P is the sum of sizes of, actually I can get full screen now. It's the sum of sizes of the trees. So for n equal to 4, first you would have, for first leaf, you would have just this segment tree, also with pointers to null. Then for the second one, this segment tree, this one. So each of them is log of n size, and the sum is n log n. Then, so this is initial potential. And when we merge two trees, every time that we go recursively, like 2 times, to the left and right children, so we let's say increase the number of operations by 2. It's a place where there were vertices in both left and right tree that we merge, and now they are merged to one vertex. So if I do x extra operations plus x operations, then what I have from that is P decreases by x. And because P can't go below 0, and it is never increased, because we just merge trees, we don't create new vertices, the total number of operations will be n log n. So this is this way of proving amortized complexity is something where you create potential some value that is the sum of sizes, something like that, and we notice that for every operation that we take, something decreases by 1, this potential. Here it was the sum of sizes. And then if we know that it can go below 0, because at the end it should be just O of n, I guess, or maybe, yeah, like no, the sum of sizes for sure can be negative. Then the number of operations is limited by n log n. So this is our complexity. Also, an extra thing is that you can get linear memory complexity if you compress the paths, but just like it also happens in some string problems that you have to do it for a try, but it isn't necessary. Am I going to write the code forces round? No, I'm not. +1. Yeah, so the segment trees I talked about are for merge sort. So one possible implementation of merge sort is that, well, if you want to count inversions in general, you can store the elements that are on in the left interval as leaves in the segment tree, and this way you are able to answer queries, what is the number of elements smaller than something. So for example, consider the following problem. You have a sequence and you must process operations. Add element to this sequence and give me the number of elements in some interval. This can be done in segment tree, exactly this way. And now it's time for the last problem. The last problem is temperature. I remember that I didn't advance to the finals back then because I didn't understand this problem correctly. So this problem is about finding the maximum subarray that does something, the longest subarray interval, while I tried to find the subsequence of maximal size, so not necessarily consecutive, and that's bad. And unfortunately, the samples didn't catch that, the sample test. So this is why I didn't advance to the finals. Of course, this is my fault. Like the statement was clear about it. So the problem is we are given a sequence of n intervals. N is up to 1 million. Every interval is a pair of values. And we know that we must consider a sequence of temperatures where on the ith day the temperature is between these two values, then second day between these two values, and so on. And we ask about the period, the interval, with the longest possible interval with increasing or, well, non-decreasing temperature. So this is problem temperature. So what we are given is those intervals. For each of them, we mark a point. We choose a temperature on that day in this interval. Maybe it would be here, let's say it's an 8. Here it's 3. Here it's 5. Again 5. And I don't know, 7. And if we choose it this way, and here maybe we choose 3. If we choose it this way, then the longest interval with non-decreasing values is 4, because here we have values 3, 5, 5, 7, so it's non-decreasing. A reminder, by the way, if you want to take part in Code Forces contest round today, you must register now, because in 4 minutes the registration is over. Still, I will try to finish before the round so we can join there. And if you can't watch me and you want to now close, then remember that on YouTube you can watch the video later. So no worries about it. And here, what we do. So what if we just have a sequence of values like 8, 3, 5, 5, 7, 3, then it's very easy to compute the longest interval, because we just have some start of interval. We check whether the next element is not smaller than the previous one, and if yes, then we extend the interval. So we extend it. Eventually we see that the next value is smaller, so we start from a new interval. And in the process, the longest interval we ever have is the answer. Here it's of course harder. And if we ask about some interval and we want to know whether this interval is good, and now good means we can choose such values that the sequence here is not decreasing. So the task is find the longest good interval. Then, so is this good? Is this interval good? Well, if we want to choose those temperatures, let's choose the smallest possible first value. If we choose greater one, then it's only better to choose smaller one, because greater one can only block us in the next step to choose some temperature. We can always, if we have some solution, we can always change the first temperature to be lower. Then here also let's choose the smallest possible one. Then in the next interval, we can't choose 2 because it's smaller than 4, but I can continue with 4. And here it's a 6. So every next temperature is maximum of the previous value, the previous temperature, and the lower limit here. And so I say that the temperature T of I is maximum for this interval that we consider, is max of T of I minus 1 and let's say L of I. So let's say that this is L, this is R. So the interval, each interval is L to R. Or you can think about it as low and high. Now, so the issue happens if the next interval, so here we can't continue from the 6 here, because even this value, the greatest value here, is smaller than this one. So it's bad situation if Ri, so this one, this is Ri, is greater than T of I minus 1. And T of I minus 1, let's notice that it's just maximum, here we can notice that, just maximum of values L so far. So when we process, for example, this part, T of I will be just maximum of L here. So bad situation means, Ri is greater than the maximum of values in some interval, values L, let's say J, for J up to this moment. So it's bad if this maximum is, sorry, it shouldn't be smaller. It should be? Yeah, it should be smaller here. Smaller, smaller. So I think I can remove that. So it's bad if this maximum is greater than Ri. So it's bad if at least one value L is greater than R. So Ri, if it's smaller than some Lj on the left, J is smaller than I, then we can't choose proper temperatures, because we have an interval. It means that we have an interval like that, and then we have an interval like that, where this L is greater than this R. Then obviously we can't choose good temperatures in these two. So now the problem becomes find the longest interval where every R is greater than or equal to all previous L's. And if you think about this one, about this definition, then it's easy to prove that two pointers method will work. It's generally a good idea if we should find the longest interval. because so the two pointers method or caterpillar can be used if we have, so let's say for this beginning we have some longest possible sequence, then we want to say that for the next beginning, so for this is some starting index I, then here for I plus 1 we can still get this segment, so this is still okay, and maybe we can even expand that to the right, then two pointers will work. And here it's true, because if in this interval there is no pair of indices I, j such that this happens, then it's also there is no such pair of indices also here, because it's a shorter segment. So we can use two pointers. And so what we can do to get first, let's first talk about n log n complexity. To go do n log n, we just need to know whether we can expand one more element to the right. So we take a look at this Ri, and we want to compare it to maximum L here. So here max L. We can answer this in logarithmic time with segment tree, or in constant time actually with something that is quite with RMQ, but it's quite slow. And this will work. This is already a working solution in n log n. Again, it's hard to say without time limits whether this would pass. So we just move with two pointers, starting one, ending one. To know whether we can move the next pointer, we compare the next Ri with the maximum L in this interval. If this R is not smaller, then we expand by one, and so on. And finally, when we can't, we move the first pointer by one. And the alternative is to use the technique that is, let's call that sliding window max. So if we just care about maxima in some intervals, then we can update them in constant time, well, amortized O of n, when we just move a sliding window. So this is just some extra technique that will allow you to get rid of logarithm, and with that we will get O of n complexity. How to do this? So we have some values. We work with values L because we only care about the maximum of L in some interval. When we have some sequence and we have some interval, then we want to store in a deque or some stack maybe all interesting values. So such values that there is nothing greater on the right, and we can treat that as a stack, and we can update that when we move to the right. So that is a short description. If you want to attend in Code Forces round, this is now a time to go, and what I will do in the next few minutes is I will explain this technique in detail. So good luck to those participating in the Code Forces round. Yeah, have the people left stream in the last 10 minutes. This is not strange because the Code Forces round starts, but they can watch me later. So this is second. I don't need this. So what we do is, so if I store these indices, then I want to say that the first of those is the maximum. So this is the current max. And what happens when I add a new element? So I want to expand my interval by one. So I add this new element. Then on my stack, I remove the last element if it's smaller. And this is my new last element. It's a similar thing in convex hull, by the way. And also, what happens when we want to remove the first element, bad color, when we want to remove the first element, so we remove this one, well, just we don't have to do anything except for removing this first value from the stack or some structure with these indices with in pink or red, because this is a new max. So we store these indices that create a decreasing sequence, and we know that if the first of those will be removed, then the next of those will be the new maximum. Here we don't store. Why don't we care about this green element? Because it's anyway smaller than something on the right, this one, the current max. So even we can skip that and not care about its value, like never, because even if, like, when we move with this start of the interval to the left, it will anyway be removed earlier than the maximum here. So this will never be maximum, because from now on, all the time it's smaller than the next element. And eventually this will be removed and this will still be greater. So we can ignore this green element. So that's the technique. I will show you my implementation. Submissions. And now what we have here. So I read the input, then indices is that kind of stack. Vector start is, so vector doesn't allow me to remove the first element. Actually, what I should use is deque, but deque is quite small, quite slow. So I wanted to use my own structure. So this is just an index where the first non-removed thing is in indices. Instead, I could just, so by moving this by one, I kind of do remove the first element of vector. So this is that pink stack. Answer I initialize as 1 because the size 1 is always possible, so it's not bad to do it. At the end I will print answer, and in the process I use two pointers technique. So what I do is I start with the start at 0. A is the first pointer, B is the second pointer. And now so I move with B. Now when B is increased by 1, I remove some of last elements from the pink sequence, from the indices. So this is what happened here. I removed this one because it was smaller. So let's see here. Indices of back, so this index, the input value of that, so this means L of indices of back, was smaller than new added L, new added value. So we remove this. So here I do indices pop back. Then I do this in a while loop. I push back B. And then I move the start. So what I do is I want to move A. I have a while loop here. Oh yeah, so here I have some value. Oh, sorry, not here, but I read in of B of second. So this is R of B. Let's remember that this is something. So this is this new R that should be greater or equal to max L here. And while this is smaller, what is forbidden, than the first value in the stack, I move the first pointer to the right. So if indices of vector start was the first thing in that stack, then I move A to that index plus 1, and I remove the first thing from the stack. And I maximize answer with the length of interval from A to B. And this is the end of this solution. What I think I didn't talk about in the previous, some of the previous problems, one more thing I want to get back to. So I said that I will explain add edge and remove edge, and I didn't do it. Here it is. So for a problem where I wanted to remove edge from two sides, what I stored is edges is just list of neighbors, and also where opposite, when I know that for vertex A, vertex B is somewhere, let's say it's 5th in the list of neighbors, then I want to store there also only, well, I want to store not only that vertex B, but also for B in its list of adjacency, in its list of neighbors, which one is A in this list, the index of A, to be able to remove that. And then in remove last edge, so I read B is edges of A of I. I read J, meaning in the list of neighbors of B, where is A, and then I change these two to -1s. So this is just something that I forgot to say earlier. That's it. We solved all 4 problems. So I competed in that contest many years ago, and I didn't succeed. So temperatures was a problem that I think I would solve if I read the problem correctly. So I advise you to read statements well carefully. And that's the end of today's stream. The next one will be, I think, a boring stream where I prepare just the materials for the next lecture, I guess. And maybe also in a week from now, I will do upsolving of the AdCoder problems, AdCoder contest on dynamic programming. So there was a contest with 26 problems on dynamic programming. I might do that. And anyway, you will see announcements about my future streams on my Facebook, Twitter, Codeforces, and in my YouTube channel. So when a new stream is scheduled, you can go to youtube.com/Errichto, and here you will see that there is a countdown to the next stream when it's scheduled. I also recommend, if you're new to this channel, to check out my previous streams and my shorter videos like this one about a non-trivial, maybe coding interview question that is kind of unusual because it's modified binary search. If you like my content, subscribe to the channel, like the video, this stream, tell your friends about them, about the videos, if you think they would like them too. And that's it. Thank you all for watching, and see you next time. Bye bye.